Hi everyone, I am Alix and I will talk about some work in progress on complete stack safety for capability machines. This is joint work with Annalyn George, Armel Guillenot, and Lars Birkedal. So capability machines are a kind of computers with fine-grained control over memory accesses. And one such kind of capability machines is the Trieu machine from Cambridge University. Beyond being a product of research, capability machines are becoming a real reality with ARM developing a prototype of a Trieu extended CPU called Morello. And thanks to the fine-grained control over memory provided by those capability machines, they are making a very attractive target for secure compilation. And as such, there has been a lot of recent work on protecting memory, either the heap or the stack using capabilities. In this presentation, I will mainly focus on the call stack. So the call stack is what is used to implement high-level abstractions such as local state or structured control flow. And if the call stack is not properly maintained, then a malicious program could abuse it to hijack the control flow or leak confidential data. There have been previous work focusing on protecting the call stack to enforce some purposes, namely local state encapsulation, fabricated control flow, and temporal stack safety by those papers on the slide. So what are those purposes? Let's start by explaining local state encapsulation and fabricated control flow with this example known as the awkward example. Its code is given in C on the left-hand side and the OCaml equivalent is given on the right. I'm going to walk through the example step by step. So f first set its local variable x to 0. Then next is going to call some arbitrary function, and to do that a return pointer to line 6 is pushed on the stack, and the arbitrary function can do anything with the rest of the stack and use it at its stack frame. After the calls return, f changes x to 1 and calls the adversary again. And this is where the issues start. So if local state encapsulation is not enforced, then the arbitrary function would just change x to any value and violate the assertion when it's going to return. On the other hand, if well-bracketed control flow is not enforced, then the adversary could keep a copy of the return pointer to line 8 anywhere in memory, so either on the stack or on the heap. So in this drawing, I kept the copy on the stack. Then the adversary can decide to call f instead of returning. And since the variable x is static, then that means that when f is called, then it's going to set x back again to 0. And the adversary is called again. But this time, the adversary has access to the return pointer to line 8, since it kept a copy from a few steps before. So then it can go back to the assertion, and the assertion is going to be violated since x is now set to 0. Now let's see what temporal stack safety is. In this example, main has a local variable x, and it's going to pass its reference to f. F uses this reference and store inside a reference to its own local variable z. The issue is that after returning, this reference stored in x is stale. Now, if the main function calls the function g, which used some memory padding, and calls the function h, which is used to write to some reference that it is given, it's possible that the reference given, which is x here, is actually going to coincide with where the return pointer is supposed to be stored. And in that case, if instead of writing 0, it was some other address, it could lead to jumping to some arbitrary code and then hijack the control flow. So as I said, the issue is really that it should not be possible for a reference to point to some stale location, as X does in this example. So while combining wire-bracketed code overflow, local state encapsulation, and temporal stack safety would be great, I believe this is not sufficient to achieve complete stack safety. So what do I mean by that? I want to remark that when an element is popped from a stack, it should no longer be accessible through the stack, but that is not the case at low level. So for instance, consider this function f, which has some secret and passes its reference to a trusted function. The trusted function makes a copy on its own stack frame to do some computation with it before returning. So even if f clears its own stack frame, as is often done in security critical code, the trusted function may have forcoded to do so, and so a potentially malicious coder could then read what is left on the stack. So there is some form of use after free that has not been considered so far in those work that I mentioned. So to recap on the protection mechanism that have been proposed so far, Guard and others have proposed a calling convention using local cavities as can be found on cherry machines to enforce wire-bracketed control flow and local state encapsulation. But it does not enforce temporal safety nor protect against the use after free issue. And furthermore, it is not possible to use in practice as it requires way too much memory clearing. They then propose to use linear cavities to enforce the same purposes, but it is believed that linear cavities cannot be efficiently implemented in hardware. Then SUMPAS and others have proposed so-called lifetime cavities to enforce temporal safety. I believe that they might be too costly to implement in hardware. And finally, Georges and others have proposed a new kind of capabilities called uninitialized capabilities and used it to improve on the first calling convention and made it fairly efficient. But the issue is that even if we combine a local uninitialized and lifetime capabilities, it won't be enough to solve the use after free issue. So let's see what those capabilities are. First, regular capabilities are just unforgeable tokens of authority. They have a given permission, such as read or read write or read write execute. They have a range of authority between two bounds, for instance B and E on the picture, and a current address it's wants to. So for instance, in the picture, the cavities is going to have the permission P over the whole range between B and E, and it currently wants to some address A inside of the range. And local capabilities are, to simplify a bit, just capabilities that can only be stored on the stack. And if we go back to the awkward example that I talked about, the issue was that for wire-bracketed control flow, the adversary could keep a copy of the return pointer either on the stack or on the heap. But if the return pointer is made local, then it can only be kept on the stack. And as Skarsgård and Cortez have noticed, if F just clears the stack before calling the adversary, then the issue is solved, since the adversary will no longer have access to the copy of the return pointer. But this is obviously too costly in practice, since you need to clear the whole stack. So to implement this, Georges and Cortez have proposed uninitialized capabilities, which are new kind of capabilities such that they have a regular permission on the initialized part between B and A on the picture. And they have a write only permission on the uninitialized part in gray in the picture. And the boundary is going to change each time that A is written to. So, and uninitialized cavities can be leveraged so that the memory clearing in the previous slide is not necessary anymore, which makes the current convention much more usable in practice. And finally, lifetime capacities are capacities that are annotated by a lifetime, represented by a number, which is the call depth of the function that owns the capability. So the idea is that capabilities with shorter lifetime cannot be stored using capabilities with longer lifetime. So for instance, if you remember the previous example that I gave, the variable z owned by f would be represented by a capability with lifetime n plus 1, and x is owned by main, so it would have a capability with lifetime n. And since n plus 1 is greater than n, then that means that it has a shorter lifetime and cannot be stored where x is. So this will obviously enforce temporal safety, since the issue was that x would point to a stale location, and this is not the case anymore. But to solve the use after free issue that I mentioned, we need to be able to stop the caller from keeping an alias with read authority over the whole stack. And even by combining all those capabilities, it is not sufficient to be able to enforce this. So what I propose is a new kind of capabilities that we call monotone capabilities, which I believe can be implemented in hardware. The idea is that since the stack is always growing in one direction, we can leverage this information. So in this picture, the stack grows toward the top. And so if a cavity can be used to read higher than another cavity, then this cavity has implicitly shorter lifetime than the second cavity. So for instance, in the picture, the cavity is uninitialized and can read up to A1, which is higher than A0, so it can be stored at address A0. But if it was not an uninitialized capability, it could be used to read up to E, and similarly, since E is greater than A0, it could not be stored at A0 either. So this obviously guarantee temporal safety, as it can be seen as some form of coarse lifetime capabilities. But we also obtain other property, which is that if a function owns a capability, a monotone capability with read authority over some range, then necessarily any other capability also with read permission over that range must be stored above. So a courier cannot keep a copy or an alias of this over this range, and only couriers can, but then this becomes the same issues as the return cavities that I presented earlier, and we know how to solve this. So to finish, there's a lot of exciting work focusing on protecting memory safety, and especially the call stack using cavity machines. But the proposed protection so far are not sufficient to achieve what I believe to be complete stack safety. And I propose a new form of capabilities to solve this issue. This is still work in progress, and we are now working on formally proving that this proposition really works. Thanks for watching.